Here we are again. Hello. Hey, it's section 3.10. I know we're getting close to the end of the chapter because we're into linearization of a function. So that's what section 310 is about. There's two concepts that we're going to study: the linearization of a function and the differential of a function. And everything fits into one picture. Basically, all of this is dealing with how the tangent line can be used to approximate the function, whatever you're dealing with, in a small neighborhood. Well, how do we want to say this? All right, small neighborhood of the point of tangency. All of that to say that you can use the tangent line to approximate the function if you're really close to, say, a. So a drawing is really what's good. Before I get to that drawing, let's not let this get lost. Here is the formula for the linearization. That's the linearization of a function at a point a, f of a. Okay, so the picture I'm talking about that really helps to see this, good luck to me drawing it, but I have an idea of graphing f that way, and then you'd have a tangent line, and it would be an arbitrary a, whatever you decide to put it, wherever you wanted to put it, and the tangent line, you know what, I'm going to draw him in black also. I don't have much of a choice. I haven't learned those colors yet. But anyway, there's the tangent line at that point. And you know what that is? That's L of x. That is your linearization function. Okay? Now, in red, what happens is if you go a little ways away from A, let's say that this distance here, we give it a name. Well, you know what? It's the x-axis. Let's call it delta x. Then to figure out the actual value of the function there, which would be, say, f of a plus delta x. Let's get that one right. F of a plus delta x. You could do one of two things. You can plug into the function, of course, and figure it out. But if you use the linearization function, which is really just a straight line, we did this since the beginning of the semester. It is the straight line, find the equation of the line of tangency, or the tangent line. That would be L of a, plus delta x. Okay. So we have different values. I'm going to draw this in as best I can. This is f of a. Okay. So the linearization is the tangent line itself at a. The differential story, and there's a formula for it down here, right here, the differential. That's a weird looking thing, isn't it? We'll get to that guy. The differential is really the difference in y, the change in y. So it's kind of microscopic. Maybe if I made this a little bit bigger. Hey, I can do that. What do you know? Then I'll have to shrink it later. So it's larger. Okay. Well, this change right here, that's the difference in the actual difference in the function values. That is f of, better write this small, a plus delta x minus f of a. And we call that delta y. That's the change in y along the function. But you also have this other piece that's not exactly the same size, and that is L of a plus delta x minus f of a is equal to, they give it a different name because it's a different value, dy, and that's the differential. It's the change along the tangent line. What would the instantaneous rate of change tell us about that? Okay, so if you know anything about, let's say, derivatives and equations of tangent lines, it goes something like this very quickly. So you have a point, which is a, we're going to develop this formula right now, a f of a. You have a slope, and the slope m tan is f prime of a. Therefore, the equation of the tangent line is given by this. Y minus f of a is equal to f prime of a, that's the slope, and then x minus a. What you get is y equals, or why don't we put it in here, call it L of x equals f of a plus f prime of a x minus a. That's the formula for the slope, the going along the straight line, not going along the curve. Okay? The other part of this that I'm going to develop comes from, let's do it down here. Okay? So we're looking for the dy. dy, the way I've got it set up, is L of a plus delta x minus f of a. Well, we know what L of x is, okay? So whatever you plug in there, away you go. So what we would say is it's equal to f of a, okay, let me get this right. Yeah, f of a plus f prime of a times, we're going to plug this in for x, a plus delta x minus a. So we're really getting f, and then minus the f of a at the tail end, this guy. Okay, we're trying to find the difference between the linearization value and the actual function value back at a. So in other words, the dynamic is this. If you start at a and you move a little bit with x, what happens to the function value? What happens to the linearization value? What we're looking at right now is the change in the linearization along the tangent line. So we're going, okay, I'm going to take this L of a plus h, which is right here, we had it, and I'm going to subtract from it f of a, and I'm going to figure this out. Well, what we're getting is f of a plus f prime of a, and then the a's cancel times delta x minus f of a. So dy is turning out to be, the change along the tangent line is cancel. It's going to be f prime at a times delta x. Great. Now that's good for a, but if you go for any x, that looks like say, for any x value, you get dy is equal to f prime of, I don't care about a, just call it x. And then the delta x, well, that doesn't change. What happens is that's the same as dx, so we're going to say those two are the same name and call it dy is equal to f prime of x dx, because it turns out those guys are two names for the same thing, the change in x. Here's the thing. The change in x is whatever it is. The change in the function value is delta y. The change in the tangent line value is dy. And there you go. There's the formula for the differential, which is really weird. It's easy to figure this out. And anytime they tell you to find the differential, it's really easy. Because aren't we used to dy dx is equal to f prime of x? It's a different name for the same thing, right? But now we're writing it, hey, as if you can detach that dx and write dy is f prime of x times dx, which is really weird. But it's really important for us to know that the differentials are really infinitely small, infinitesimally small change in y and x, okay? They used to call them in the old days infinitesimals or something like that. So we have a formula for both of these guys, and that's the development. The last thing I'll do on this video is go through these questions, and then I'll stop and I'll do another video for 2 more problems from this section. And this section will be done. Okay, so here's how you do this. This is just a lot. This is me playing around with the homework, but a lot of this is homework problems. It says find the linearization of this function. Of what function? This guy up here. We are given that f of x is cosine of x. We are given the function cosine of x. Find the linearization of this function. There's two things they have to give you. The function itself, and guess what? A. So the first thing we do is the function, for number 1, f of x is cosine of x. And also we are interested in the point of tangency when x is equal to a is pi over 4. For those visual folks like myself, you've got the cosine function, and if you cruise on over to pi over 4, you got a point of tangency, so our tangent line is pointing downward like that, okay? The linearization, it's straightforward. You just go the linearization. The formula says do f of a plus f prime of a and then x minus a. Well, we know what a is. We don't have f prime, but he's easy. Here we have cosine. My writing is terrible. But since we have this, we know that f prime of x is equal to negative sine x, right? So the linearization does this. It wants you to plug in a here, a here, a here, and a is pi over 4. So L of x at a is equal to pi over 4 is this. F of a is cosine of pi over 4. F prime of a is minus sine of pi over 4. And then you have x, which is your lone variable, minus pi over 4. All right, so our linearization function is, looks like I'm getting a radical 2 over 2 minus radical 2 over 2, x minus pi over 4. Now take a moment. That's our first answer right there. That's a linear equation, isn't it? That's a linear equation. I've got this number, but I've got a slope value. M is minus radical 2 over 2. That's actually a straight line equation. 2 says, use this linearization function to approximate the value of cosine. This is where the homework kicks in some more, and you know, I need to approximate cosine of 48 degrees. Okay, the way you do this, remember this picture way up here, is we're going, let x change a little bit right there. Let's go to a number line for this problem. It's really good to do this. You're going to go to 48 degrees. I'm going to actually expand that and go, okay, here is pi over 4. You know what that is? Let me get rid of that. Pi over 4 is another name for 45 degrees. So if we jump over just a little bit more to 48 degrees, okay, that you can change that. You can put it into radian measure if you want, but I'm going to show you something different instead. Okay, in fact, I'll do it right now. The story is, with this information, we know what delta x is. Delta x is 48 degrees minus 45 degrees is 3 degrees. This is when I change it into radian measure. And as it turns out, that radian measure, how do you do it again? Oh yeah, multiply by pi over 180 degrees is actually pi over 60 radians. That is delta x. Why is that important? You'll see. Okay, so we're going to use the linearization function. You thought I'd start right with that, huh? Well, the linearization looks like this. L of 48 degrees. In fact, I'll color code it so we can see that better. 48 degrees is equal to radical 2 over 2 minus radical 2 over 2. And then here you go. 48 degrees minus pi over 4. Oh, that's interesting. I wondered why you did the delta x. Well, that is this equation right here. All of this is really just pi over 60. That's why I did it. I guess I have some experience with this to make me do that instead. So what we're getting is L of 48 degrees is equal to radical 2 over 2 minus radical 2 over 2 times pi over 60. And I approximated that with a calculator. and got 0.67008 roughly. So it's about, 0.67008 whatever. And that, listen, this is the linearization. It approximates, this is an approximation of cosine of 48 degrees. It's not spot on. Later in the problem, we'll figure that out. Okay, so that's our second answer. Let's go to 3. 3 says, find the differential of cosine of x. Okay, this is an easy one. dy is equal to f prime of x dx. So dy is equal to minus sine x times dx. We're done. That is the formula for that. Okay, pretty crazy. All right, that's a formula for the change along the tangent line. Okay, there's two pieces to it. X is where are you situated, and dx is how much did you change. Let's see the next problem. Find the value of this differential for x and dx as given in problems 1 and 2. Well, here's the number line. Here we are at pi over 4, and then we jumped a little bit farther. I know this is 45 degrees and this is 48 degrees, but the jump that we made is pi over 60. Guess what? This is going to play the role of x. This is going to play the role of dx. We start here and we move a little. So what this differential is doing is it's telling us the change along the tangent line. We're changing from 45 to 48 degrees. We're changing from pi over 4 to pi over 4 plus pi over 60 radians. So we're getting a minus sine of pi over 4 times, and now pi over 60. Okay, so what that means is we have, a negative radical 2 over 2 times pi over 60. And when you plug that one in, let's see what I got for that one. I got a negative 0.03702, so it's a negative 0.0370, something like that. 3702, and it kept going. I'll box that in and say, there you go, thank you very much. Why is it negative? Why is it negative? Because when you go to the right, your y value goes down a little bit. That's why it's negative. It's all right there in the graph. That's why the graph is good to know. All right, number 5. I'm trying to cram this into one video so you can pause it and rewind. Compare the approximation in problem 2 to the real value of cosine of 48 degrees. Okay, so the approximation in number 2 is this guy. Okay, so what I'm going to do for number 5 is I'm going to take L of 48 degrees and subtract from it using a calculator. This is kind of plain. This is Richard Weber playing around with this a little bit, maybe on a test or whatever. Okay, so compare these two. This is an approximation, and this is the real deal. Well, when you plug in, you're going to go that 0.67008 or whatever minus your actual cosine value, which is 0. What did I get? Oh, I'm supposed to just compare it. Okay, never mind. So it just says compare the approximation, and it goes found with a calculator. So forgive me. All right, so I have to play the game right. Almost done here. So this one we found to be 0.67. Where are you again? It's right there above. 008, and change. Okay. Compare with the actual cosine 48 degrees, and that turned out to be, with a calculator, 0. Where are you? 6691306. 0.6691306. 1306 and other stuff. How do they compare? 0.67, 0.669. They're very close. Well, we didn't move off much, did we? So the last problem, 6, is an interesting question. It goes, how does the differential fit into all of this? Okay, the actual differential. Well, this is where I think I did the following. I did L of 48 degrees. I'm just going to show you what's going on. Minus cosine of 45 degrees. So this is the actual place we started, but we bumped up 3 degrees, And we're just looking at the difference here. When I compute it, I get this is equal to that 0.67008 and all that stuff, minus radical 2 over 2. And I computed it and got, guess what, negative 0.03702 or whatever. And it is identical, of course, to dy. So dy is equal to the change along the tangent line. There's a lot in this video, and a lot, you know, if this was a lecture, you guys would be raising your hands and pausing me, but you can pause this video anytime you want. But this is what I wanted to show you in the first one of these guys, and it was a lot to it. There's the development and then having fun and games with those problems. I hope this makes sense, and it's time to pause this particular video. And thanks for listening. Let's see.